Welcome to Hi-Fi, a high-yield physics lecture series to help you become a better radiation oncologist and help you pass boards. In the last video, we talked about the factors affecting dose calculations and the reference or normalization conditions typically used to calibrate a LINAC. These include an SSD of 100 centimeters, a field size of 10 by 10 centimeters, and the calibration point at D max. The machine is calibrated to deliver 1 centigrade per monitor unit to the reference calibration point for each individual beam energy. If we were prescribing the dose to the calibration point under this setup, the number of monitor units would just equal the dose in centigrade. In this case, our formula would simply be prescribed dose over calibrated dose rate. However, since our treatment conditions are usually different than the reference conditions, we must account for these changes. This video will work through some examples of hand calculations for clinical setups. First, let's take a second to review some of the key points we talked about in the last video. Specifically, we are going to consider how PDD and TMR are impacted as each of these parameters increase. Increasing prescription depth means decreasing PDD and TMR, meaning we would need more monitor units to deliver our desired dose. Increasing beam energy means increasing PDD and TMR, meaning we would need less MU in order to deliver our desired dose. Increasing field size means increasing PDD and TMR, meaning we need less MU in order to deliver our desired dose. We treat patients with either an SSD or SAD setup. For an SSD setup, PDD is used in calculations to determine the monitor unit required to deliver the prescription dose. This accounts for both inverse square and tissue attenuation. Therefore, changing SSD directly impacts PDD because the inverse square component changes. For an SAD setup, inverse square is typically not needed since the calculation point often remains constant for this type of isocentric setup. Determining the monitor units required to deliver the prescribed dose generally only requires the use of the TMR. Tabulated TMR data is not dependent upon SSD. With this knowledge, we can develop a formula. Each of the discussed modifiers impact the dose reaching our point or target of interest, so they go in the denominator of our formula. Therefore, our formula becomes dose in centigrade divided by output factor, the depth dose correction, the inverse square factor, and any other modifiers such as off-axis ratio, tray factors, or wedges. We will walk through these factors quickly, but right off the bat, let's remove the wedge, tray, and off-axis ratio correction factors. They would go in the denominator, but we'll skip them here to concentrate on the main points. In addition, for emergency treatments based on hand calculations, best practice is not to use a wedge because errors in the factor can be sizable if done incorrectly. These factors are also unlikely to show up on exam questions, but if they do, you'll know where to put them. The collimator scatter, or S sub C, and phantom scatter, S sub P, together are termed the output factor. The output factor will account for the change in dose rate due to field size. The depth dose correction factors of PDD and TMR values will be needed for the SSD and SAD setups respectively. Physicists measure each of these values, the output factor, the PDD, and the TMR, during commissioning of each LINAC and generate lookup tables, which are used to perform our MU calculations. The nuanced thing here is the inverse square factor in the denominator. You need inverse square if the calculation point is not the same distance from the source as the reference point. In other words, if your SSD is anything other than 100 centimeters for an SSD setup, using a PDD calculation, or a calculation point is anywhere other than 100 centimeters for an SAD setup using a TMR calculation. Both the reference location and the calculation point location would be clearly communicated in an exam format, but most exam calculations and the majority of clinical calculations will be set up so that either SSD is 100 or the calculation point will be at SAD. If the calculation point was at a different distance from the source than the reference conditions, you would need an inverse square correction to adjust the output accordingly. However, this is outside the scope of this video. This discussion emphasizes that the first step in any MU calculation is to understand the reference conditions used in your clinic or in your question stem. We've also emphasized that a PDD calculation uses an SSD setup. Here's the formula we would use for this scenario. Dose goes in the numerator and modifiers go in the denominator. We had mentioned our beams were referenced at Dmax, and for SSD setups, we would be using a distance of 100 centimeters. So you can see that the inverse square factor would equal 1. For an SAD setup, dose goes in the numerator and modifiers go in the denominator. In this case, if our reference conditions were for SAD setup at 100 centimeters, you can see that inverse square factor would equal 1. Now let's consider examples of urgent weekend treatment setups and hand calculations. Say you're consulted on a patient with cord compression at T4, needing emergent treatment. This particular clinic has calibrated their machines to deliver 1 centigrade per monitor unit at Dmax with SSD setups. You've set up the patient and decided on a dose of 300 centigrade per fraction with a single PA field and an energy of 6 MV and a 100 centimeter SSD setup with a target depth of 6 centimeters. You're planning to treat one vertebra above and below T4, making your field size 6 by 8 centimeters. How many MU are required to deliver the intended dose to your target? First task, understand your clinic's reference conditions. We are told this clinic's reference conditions are to deliver 1 centigrade per monitor unit at Dmax for a 100 centimeter SSD. This will make our monitor unit calculation easier since we are using an SSD setup and the inverse square factor will therefore equal 1. In this case, there's only one beam, so we put the total fractional dose of 300 centigrade in the numerator. We'll use PDD here since this is an SSD setup. The PDD and output factor will be obtained using the clinic lookup tables once we have the equivalent square field size. Remember, equivalent square is equal to 4 times the area over the perimeter. In this case, we multiply the area of 6 times 8 by 4 and divide that product by the perimeter of 28, which is roughly equal to 7. Now we can look up our PDD by finding the cell corresponding to the equivalent square field size of 7 centimeters and a treatment depth of 6 centimeters. We find the PDD is 0.797. Likewise, we find the output factor for a field size of approximately 7 centimeters, which is 0.944. Note that here the output factor is smaller than 1. This is because the field size is smaller than a 10 by 10 centimeter field, which is where the output factor is defined as 1. Putting this all together, 300 centigrade goes in the numerator and is divided by the output factor of 0.944 and the PDD of 0.797, which altogether equals 399 MUs. You should always make sure this calculation makes sense. For instance, if your calculation yielded 600 MU for a prescribed dose of 300 centigrade, we should instantly smell a calculation error and recheck our inputs. For the next case, you are called to a clinic across town and need to treat a patient with multiple brain metastases urgently over the weekend. Remember, the first step in any MU calculation is to understand the reference conditions. You are informed this clinic's reference conditions are different than the previous clinic. Their reference conditions are 1 centigrade per monitor unit at Dmax with a 100 centimeter SAD setup. You plan to deliver whole brain radiation. The patient's head measures 16 centimeters in separation, and the field size is 13 by 15 centimeters. You prescribe a dose of 300 centigrade for the first fraction with opposed lateral beams and an SAD setup. You select a beam energy of 6 MV. How many monitor units are needed from each lateral field to deliver the prescribed dose to isocenter? Again, first step is to check our reference conditions. For this example, reference and calculation point are the same at SAD of 100 centimeters, which makes our equation easy since inverse square factor will equal 1. Since we are treating with 2 beams and an SAD setup, implying the isocenter is in the center of the brain, each beam should deliver half the prescription dose, or 150 centigrade. Now we need to account for the variation from reference conditions for the TMR and output factor. Again, we will need the equivalent square field size and treatment depth to look these values up. For a hand calculation with an SAD setup, depth is half the separation of the head. so 8 centimeters in this case. The field size must be converted to an equivalent square, so the area of 13 times 15 is multiplied by 4, and then divided by the perimeter of 56, which altogether gives us about 14 centimeters. Now we can use our lookup tables. For TMR, we find the cell corresponding to our depth and our equivalent square size, which is 0.844. And for the output factor, we just need to find the cell corresponding to our equivalent square field size, which is 1.05. Note that here the output factor is larger than 1 because field size is larger than 10 by 10 centimeters. Putting this all together, we have 150 centigrade divided by our output factor of 1.05 times the TMR value of 0.844, which altogether equals 169 monitor units. So each beam should deliver 169 monitor units, for a total of 338 monitor units per fraction. For those gunners in the front row who have noticed our clinics conveniently use reference conditions that are the same as the respective treatment setups, good catch. It is important to note all clinics will not choose the same reference conditions, and as long as you know to use the inverse square factor when they don't match, you should be set. We don't have time to go through both these calculations again, but if you want to go back and calculate these two problems with alternate setups, be our guest.